I'm just going to be doing a quick question on Doppler. Oops. Oh, it's the wrong note, someone. Right, so I'm just going to go to my, I think I picked out the questions, a 2008 paper one. Yeah, you'll find some of the older questions are quite nice and more interesting. So it's going to be on the Great Child Tuition. There we go. Okay, dope. 2008 exemplar, right? So you can find these papers on the internet, I hope, right? So pretty interesting question. The sketch below shows a stationary ambulance. So what we always like to do when you're starting a physics problem, right, is non-negotiable. You have to have a schematic. What do I mean? You have to have a small, simple diagram. Then you need no artistic ability as long as you differentiate what you're doing. It's very important that you understand and you can visualize what's going on to separate the scientific phenomena, so you know how to apply the equations and all of that, right? So we have these tools. The methodology is very important. So we have the stationary ambulance. I'm going to do my best to draw an ambulance. I'm not going to be very good at it, but should be fine, right? That's an ambulance. Don't judge me. Put a big nice cross there, ambulance, and a siren, right? Let's have a siren, wee, right? Yeah, whatever. And the ambulance is emitting the sound. Okay, and it's going to reach this car according to the question. The siren emits frequencies, etc. Driver of a car approaching the ambulance, right? So the driver approaches the ambulance to a nice car. That's the best I can do. I'm sorry, I'm afraid. Yeah, okay, that works. So you should see my mosquitoes though. I draw really good mosquitoes. And that's yeah, see my mosquito really good. Anyway, so this is approaching. It's approaching the ambulance at a certain constant velocity, which we do not know. And it's the listener because it's going to be experiencing the frequency, right? So this on the top, you'll write FL, F of the listener, frequency as observed by the listener, right? And that's going to be a certain value, which we'll find. And the ambulance is stationary, according to the question. Give it a quick read. 0, right? Now, the ambulance is emitting a frequency of 700 hertz, right? So F of the source is 700. Now, at constant speed, the frequency of the emitted sound waves change by 80 hertz. So 80 hertz is the Doppler shift. What is the Doppler shift? Doppler shift is the, I can stand to do a quick theoretical approach here. So Doppler shift is simply the difference between the actual and the omitted frequencies. Okay, what does that mean? Let's get this quickly. What does that mean? So you know that's situation where you have the sound waves propagated by a moving source. So let's draw that a bit better. Okay, by a moving source is going to, oh no. So just going to do that nice circle. So sound wave in the medium, be like that, and the next one's going to be like that, and the next one's going to be like that. Okay, so it started here and it's moving in this direction. Okay, and it's emitting those sound waves. And over here we have an observer, and we have another observer here. The observer in the front, which I'm going to call observer A and observer B. Obviously, the source is approaching observer A and moving away from observer B, and it's going to be emitting a certain frequency, a certain constant frequency, which is unchanged. Okay, but observer A will experience or hear a certain frequency A, and observer B will experience a certain frequency B. Now, theoretically, what's going to happen is we know that frequency heard by A, right, as the source approaches it, is going to be greater than the actual frequency. And we know that the frequency heard by B as the source moves away from it is going to be less than the actual frequency, right? How so? Why? Because in the first case, look what's happening. right? Sound wavelengths are being compressed as the source approaches the listener. So as the source comes closer and closer to the observer, the sound waves are compressed, meaning there's more sound waves per unit time. So there's a smaller period. Okay, smaller period. What is period? The amount of time that it takes for one full wave to move or to cycle. And that becomes smaller because the waves are coming at you faster, right? And because the waves are coming at you faster, there's more waves per unit time. That is the definition of frequency. So frequency will be high, right? Wavelength will be compressed, so small. uh, Period will be small. Frequency will be high because we know for a fact that period has an inverse proportion to frequency, right? This is the be all and end all of the section, right? And we know that for frequency A, for B, observer B, can you see these large distances, right? As the source is moving away, it's putting more distance between each wave, which means it's going to take, because sound is constant and speed through a medium, right? Through a consistent medium, through air, it's going to be the same speed, and it's moving further and further away. Look, these distances are increasing between each sound wave. The sound waves are going to take a longer amount of time, right? A longer amount of time to reach you, to actually hit you. From the time this sound wave hits you, right? It's going to be a while before the sound wave, and then a while before the sound wave, as opposed to on the left, where the sound waves are basically touching each other, so they're going to hit you very very fast in quicker succession. The word is, as opposed to here, it's going to take a while. It's going to be one, then you wait for the next one, another one, wait for the next one, another one. So it takes a longer period of time for those waves to happen. That's the definition for period, right? How long does one full wave take to occur? And it's going to be bigger. So because our waves take longer to reach there, or rather has a big period, it's going to have a very small frequency because you're going to have less waves hitting you per unit time. That's the whole thing about Doppler, really. So that's the issue. But anyway, the Doppler shift is going to just be the difference between the frequency. So it's going to be f minus fb, or f minus fa, depending on which shift you're looking at. You can only look at one shift at a time. You can't work between two observers in the same equation. We don't have the tools to deal with that, right? So the Doppler shift is going to be 80. So what's going to be the frequency of the listener? What's going to be f of l? That makes it sound like a function, so let's not say f of l, let's say fl. What's going to be fl? Fl is going to be 780. Why? Because my source, right, sorry, is coming closer to the observer. Well, the source is actually being still, but for all our purposes, it's the same effect as if our listener was still and the source was approaching it, right? If the source is approached by the listener, it has the same effect. You're still going to be reaching more sound waves per unit time, lower period, higher frequency, same issue, right? So it's going to be 780 and not 620. It would have been 620 if it was moving away from the source, right? And now we just need to solve for VL. So we put that into, oh, first we have a question, 8.1, name and state the wave phenomenon illustrated above. That's going to be the Doppler effect. Doppler effect. The Christian Doppler submitted his first this phenomenon in 1843. He proved it to the scientific community in 1845 by loading a bunch of trumpeters on the carriage of a train and making them listen to it making them hold a steady note in the carriage. And for the people waiting outside, when the train actually carriage moved past them, as it was coming, they heard a higher note, and as it was leaving them, they heard a lower note. So frequency of that sound was actually changing relative to the listener and the source as it moves away. So the Doppler effect states, um, or the Doppler effect accounts for the variation or the apparent variation in the frequency of any emitted wave, such as a wave of sound or light, as the source of this wave moves to or away from relative to a listener, right? So that's the Doppler effect. This is jargon. You just need to like by heart that and regurgitate it in your exam paper, right? So you know our steps for this. We write down the equation that they gave us, which is FL equals V plus minus VL over V plus, oh, that's a V, sorry, plus minus Vs Fl. Now we ignore it, but you write it down for that 1 mark because they look for it in the memo. Now we use our version, which is better to use, and our version says Fl equals still the same thing. It's just a variation, but it's a better variation because it's more versatile. And we put a minus, and we say Vl, close brackets. So there, the brackets help separate things, okay? V minus Vs, and then we say Fl, right? And now we can solve. We know the frequency as observed by the listener is 780. The speed of sound is given, oh, I've missed something. We put a V here equals 340. They told us that there, okay? Meters per second, always use your units. This is hertz. That's an H, my bad. Hertz, cool. Okay. We need to have 5 pieces of information on a diagram: the speed of sound, the direction the sound is moving, source, frequency, observer frequency, source velocity, observer velocity, right? So 5 pieces of information. Now we substitute here, we say 340 minus VL, the velocity of my listener, which is what we're solving for, right? But because it's now moving in the opposite direction, you see it's moving in the opposite direction of my speed of sound, of my sound. Sound is coming toward it's going to the left, okay, or rather the right, but my observer is moving to the left. So because it's in the opposite direction, we take it as a negative value. So I'm going to call it negative V, right? Can I say negative V? Yes, I'll say negative V. So 340 minus negative V is going to be 340 plus V, right? That's an important point to consider. Don't worry about why. Well, you can, but just do it, right? It makes sense. Because it's moving in the opposite direction as that of sound, we take it as a negative quantity because we're using a variation of the equation, a better one, mind you, where we have a negative in our bracket. We simply put in, substitute accordingly. So V minus, that's 340 minus V is 340 plus V, right? And at the bottom, we just have 340 minus 0, which is incidentally is just 340, times the frequency is observed by the listener, which is going to be 7. Oh, I messed this around, right? So this is going to be 700. My bad. Yeah, free F. No, this is wrong. I messed up my equation. This is going to be an S. It's going to be, so this is going to be 700. This is going to be 780. Yeah, that's fine. And now it's just some algebra. Now it's just basic algebra. So we say 780 divided by 700 equals 340 plus V divided by 340. So this is our denominator. So we can just take it and we can just multiply it here. We say 340 times 780 divided by 700 equals 340 plus V. And now we put this in a calculator, we can get a value for that into the calculator. So 780 times 340 divided by 700, and we get 378, right? We get 378.86, okay, equals 340 plus V. Now look at it, you don't need to be a rocket scientist or a paleontologist or a plastic surgeon or a gynecologist to understand that V is just going to be the difference between these two numbers, which incidentally is just 38.86 meters per second, right? Yeah, so that's V. That's how fast the car is moving. That's valid. That's very valid. Toward the, so it's going to be direction here, toward ambulance. Okay, let's check this out. Does this make sense for the car to be moving 38.86 meters per second? Let's convert our units and let's see if it does make sense. Let's convert it to kilometers per hour because I think we're more familiar with cars moving in kilometers per hour. So this is just a side exercise, 38.86. I hope you have the tools to convert. So I'm just going to show you that. Meters for every 1 second. Now I want to cancel my units, my meter per second. Okay, top to bottom. So I want to get my second on the top, but I want it in terms of hours, right? So 1 hour has the same quantity as 3,600 seconds, doesn't it? Yes, so this is the same value. It's just a factor of 1. 3,600 seconds divided by 1 hour, because it's the same quantity, it's just going to be 1, right? And then up here, and now 1 meters to be turned into kilometers. So I need kilometers at the bottom though. No, I need meters at the bottom because meters at the top here, so I need to cancel. So I know that 1,000 meters is going to be the same as 1 kilometer, right? And now what happens? Something interesting. We get cancellation. This meter here cancels with this. The second cancels with the second, and now we're now left with 38.86, okay, into 3,600 over 1,000, and we're left with the kilometers on the top, and we're left with hour at the bottom. That's an hour, right? Now this is just going to be 3.6 times 38.86. 3.6 times 38.86 is 139.89. Yeah, we can just round it off to 140. If you put your calculator, it should be 139 point some decimals, but it's going to be very high decimals, so we can just say 140 kilometers per hour. So this is feasible. Yeah, it's moving very fast for sure, but it's definitely a feasible velocity for our car, right? And that's Doppler. It's a simple question. Remember the process, remember the concepts, your definition, okay, what Doppler shift is, why we have it, and our schematic. Your schematic is very, very important. Please do this in your exam paper. The examiner will not mind. They will commend you for it because it shows real understanding. We need to have 5 things here. We need to have the speed of sound and its direction. We need to have the frequencies of the source and the listener. We need to have the velocities of the source and the listener. And then we assign directions to our source and listener, right? Or rather signs which indicate direction, right? Because in physics, you need to understand, you really do need to understand how the number line works. Sounds a bit silly, but you do. Okay, so in maths, you're taught that -5 is smaller than +5. But in physics, it's not the case. -5 is the same as +5. It's only that they are in different directions. Okay, so if I have a -2 here and a -2 somewhere there, right? This minus, oh, that's going to be +2, sorry. This +2 is smaller than -5. -5 is a bigger quantity going in a different direction than +2 because that's how magnitudes work, right? Now, coming closer to 0, though, when you approach 0, that's going smaller. And when you move away from 0, that's going bigger. So coming towards 0 is smaller, going away from 0 is bigger because the smallest quantity in physics is 0, nothing. In maths, when you have negatives, it's considered being smaller than 0 because you're going to a det, you're going to a negative, you're going to an anti-state. But in physics, it's just a different direction, well, in mechanics anyway. I hope that you're good there. So it's here, I think, right? Dismiss, and then I'm going to stop recording.